Before the beginning, a cosmic void. Imagine a darkness so complete, so absolute that it's impossible to picture. No stars, no galaxies, not even space itself. This was our universe before the Big Bang, a point of unimaginable density containing the seeds of everything we see around us. But how do you get something from nothing? It's a question that has puzzled scientists and philosophers for centuries. This state, often called a singularity, is difficult to grasp. All the laws of physics, as we know them, break down. Time and space become meaningless. It's a realm of mystery that continues to intrigue us. But from this singularity, something incredible happened, something that would birth a universe. The Big Bang is often depicted as a giant explosion, but it was not an explosion in the conventional sense. There was no empty space for things to explode into. Instead, it was the expansion of space itself. Imagine a tiny balloon suddenly inflating to an enormous size. That's closer to the truth of the Big Bang. As space expanded, it cooled and changed. Energy trapped within the singularity began to transform. This transformation was governed by Einstein's famous equation E=mc². Energy could become matter, and matter could become energy. In the first fractions of a second, the universe was an inferno. Temperatures were so high that matter existed in a state unlike anything we know today. Imagine a cosmic soup, a swirling mix of particles colliding at unimaginable speeds. Out of this chaos, the building blocks of matter began to appear. One of the most intriguing events was the creation of matter and antimatter. These particles are like mirror images, identical but with opposite charges. When they meet, they annihilate each other, releasing energy. But for some reason, slightly more matter was created than antimatter. This tiny imbalance had huge consequences, as it would eventually lead to the universe we see today. Section 4. Cooling down, atoms come together. As the universe expanded, it cooled. This cooling allowed the surviving matter particles to slow down and interact with each other. Protons and neutrons, the building blocks of atoms, began to form. The universe was still incredibly hot, but it was cooling rapidly. Around 380,000 years after the Big Bang, the universe cooled enough for the first atoms to form. These were primarily hydrogen atoms, the simplest element along with some helium. This event was crucial as it marked a significant change in the universe's properties. The universe, once opaque, became transparent. Light could finally travel freely. Section 5. Gravity's pull stars and galaxies ignite. Over vast stretches of time, gravity began to shape the universe. Tiny variations in the density of matter caused some regions to have slightly stronger gravitational pull. These regions attracted more and more matter, gradually clumping together. These clumps of matter eventually became so dense and hot that nuclear fusion ignited within their cores. Stars were born, lighting up the universe. Stars grouped together, drawn by their mutual gravity, forming the first galaxy. The universe was no longer a uniform sea of hydrogen and helium, but a tapestry of stars, galaxies, and vast cosmic voids. Section 6. An ever-expanding mystery, the universe today. Today, billions of years after the Big Bang, the universe continues to expand and evolve. Galaxies move away from each other, driven by the initial expansion that began all those years ago. We are still unraveling the mysteries of the universe's birth. The Big Bang model explains much of what we observe, but questions remain. What caused the singularity to exist in the first place? What happened in the very first moments of the Big Bang? The answers lie hidden in the depths of space and time, waiting to be discovered.